All right, our next speaker is Thijm, and Thijm is going to tell us about modular control plane verification via temporal invariants.
All right, hi everybody. Thanks for the introduction. I'll just jump right into it with some motivation. Since we're at PLDI, I'm assuming not everybody's super familiar with networks, so let's just talk a little bit about the domain we're working in, which is the network control plane. And the goal of the control plane is to determine the routes to use to forward traffic in a network. And the way it does this is using distributed routing protocols, which you can think of as a sort of generalized distributed version of solving a shortest paths problem. And the way they do this is you'll have a system, a topology, which we can think of kind of like this graph here, and we'll send some initial routes or route announcements from particular nodes, which will then be received by neighbors and processed according to configurations. And these configurations are distributed files. They're written in a vendor-specific low-level language, and they are often quite complicated, but the point is they're going to do some processing, and we're going to select a best route from the ones that we've received. And we can then broadcast that route to our neighbors and continue this process. And in a well-designed routing protocol, this system should converge to a stable state. So the critical thing which makes these kinds of systems complicated is we might want to ensure that they do what we intend them to do, but we're working with distributed files that have policies for security or traffic engineering, and we want to ensure that the end-to-end system obeys these directives. And so to do this, we need verification. So how do we actually verify these systems? Well, we take these configs, and we take these policies and the end-to-end properties that we care about, and we give them to a control plane verifier. And that verifier is going to verify all of these configs together. There's many different tools that have done this in different ways over the years. But the point here is that it's going to look at all of those configs as a unit, and then we'll repeat this process if and when configs change, like you find a bug and you fix it. So this works really well. There's a lot of, like I said, there's a lot of tools, and they've had a lot of success at doing this for a wide variety of networks. But because they're working monolithically, there are limits in terms of the size and the complexity of the network that they can consider. And some networks, like particularly cloud provider networks, are too big and too complex for these tools to verify today. And so we need a way to break the problem up into smaller problems. And that's where modular verification can help us. And so this brings me to our contributions. So we did 3 things in this piece of work. We demonstrated why a common approach from prior work of using a stable states analysis is not suitable for modular verification. And instead, we present Timepiece, which is a system based on a time-based theory for modular control plane analysis, and which uses an SMT-based verification procedure. And we evaluated Timepiece on a wide variety of benchmarks, looking at data centers and wide area networks, and found that it was able to verify properties of these networks in only seconds, whereas a monolithic tool would time out after over 2 hours. So let me start by giving a little more background on modular verification and kind of how we're going to do it and how it can go wrong. So in order for our modular verification to be useful, we need it to be sound. We want to capture all the monolithic routing behavior within our modular analysis, and that's going to be the key element that we really need in order for this to be useful. So what we'll do is we'll split our network up into node local components, and we'll verify each of these components independently. And to ensure that our individual components are accurately capturing what's going on in the rest of the network, we're going to use interfaces to represent those cross-component dependencies. And where do these interfaces come from? We're going to have a user provide them. So the user is going to look at their network. They're going to examine like the converged states of the different nodes, and they're going to come up with some over-approximation of these converged states. And they'll use a set of states to do this. And for the purposes of our talk, we'll imagine that we're using predicates to represent these sets over some variable s representing a possible state. So once we have these interfaces, we can come up with a modular verification procedure to check them. So a reasonable verification procedure one might want to use to do this is to say, I have a particular node V, and it has some neighbors, U1, U2, U3. Can I check that given routes satisfying the interfaces of those neighbors, that V will satisfy its interface? And let's see how this might work with a little toy example. This is obviously much, much simpler than your average fancy network, but it's illustrative of kind of how this might look. So we're going to abstract over what the kind of routes are going to be in this example. We're going to imagine that our routes just have two components, a local preference LP and a path length len, and we're going to try to pick routes such that they have a high local preference and a low path length, since we're trying to find short, less costly routes. And we'll also use infinity here to represent the case where there's a null route, or there is an absence of a route. And so what this little graph shows is that we have this external neighbor n, which is sending some routes into U. They can be any possible route. And we just are going to imagine that we're just going to filter those routes out for this example. And U will start with an initial route of local preference 100 and path length 0. And it's going to send that to its neighbor V. And we'll imagine that the local preference doesn't change, but the path length increases. So V is going to start with no route. And then you can all see that by the time the system converges, it's going to end up with a route with a path length of 1 and local preference 100, right? Pretty straightforward. But let's see what happens now when we try to modularly verify this system. So let's suppose we gave these weird little interfaces. We've said that n is going to send any possible route, so we just use true to represent its interface. But for some reason, we're insisting that the local preferences are going to be 200 at nodes U and V. And the problem is that that modular verification procedure I just showed you will accept these interfaces. It's going to look at this and it's going to say, oh, well, V sent a route with LP200, so U has a route with LP200, and vice versa over at node V. And this self-justification is going to mean that V is going to conclude that it has a local preference of 200, but its converged route does not have that local preference. And so our interfaces are unsound. They've excluded the legitimate converged routes, but our checks passed for this network. And this is a problem. And what we need is we need to change our model to get around this problem and bring in a temporal model. So what we're going to do is we're going to over-approximate our states as before, but instead of using just interfaces over converged states, we're going to use temporal interfaces. And these temporal interfaces are going to over-approximate the states of the nodes at a particular time t. And what we'll do now for our verification procedure is we'll have two checks that we perform, a base check, which says that interfaces should hold on the initial routes at time 0, and an inductive check, which should say that for all points in time, given routes from interfaces that hold at time t, my interface should be able to hold at time t plus 1. And using these two checks, we should then be able to hopefully do our verification correctly. So let's go back to that previous example. I've now lifted those interfaces to the temporal model by adding these curly G's. And these curly G's mean globally. We're using them kind of like a temporal operator. They say that at every point in time, the particular predicate they're given holds. And what we can see right away is with this new temporal modular verification procedure, our base checks are going to fail here because these interfaces do not include the routes at time 0. And so if we've now ruled out this bad case, and we can also prove things using these temporal operators. We don't just have G, we have other kinds of temporal operators. So if we wanted to prove something like path length, we might start with globally invariants like these ones at n and u. But now what we're going to do is if we have that u will always have a route with local preference 100 and a length of 0, we can say that v will eventually have a route with local preference 100 and length at most 1. And to do that, we use this until temporal operator, the curly u, which is going to say that in this particular example, v has no route until time 1, and then at and after that time, it will have a route with local preference 100 and length at most 1. And so we know this is a good way to do this because we have a soundness theorem. So we proved that if an interface satisfies the base and inductive checks for all of the different nodes, then it will include all states that are computable via simulation of the network. And the proof is really straightforward. It's just by induction on time. So now that we have this proof, we know we have a reasonable system, and we can use it to actually do these checks. So what we will do is we'll implement a library in C#. And what we did with this library is we allowed users to define the semantics of their network, either in C# or by importing network configurations. And then we could write interfaces in this library using our temporal operators. And I didn't show this for time purposes, but we have other temporal operators we can also use. There's some small amount of combinators for temporal operators. And what we can do is once we have all these interfaces written, we can then check verification conditions in parallel at every node using an SMT solver. So I'll now get into our evaluation. We wanted to examine 3 different things for our evaluation. First, scalability, but also how well we can handle complexity and writing invariants for different properties. And so for scalability, we looked at fat tree networks, and we scaled the size of the network from just 20 nodes all the way to 2,000. And for complexity, we looked at the Internet 2 wide area network, which has been previously looked at in other verification tools. It's a very large network. It's got over 100,000 lines of configuration code, which does a lot of complex filtering and processing of incoming routes from external neighbors that Internet 2 is connected to. And to evaluate how hard it was to write invariants for these different systems, we looked at a couple different properties, 3 different kinds of reachability property, just bare reachability, path length, and valley freedom. And then also we looked at hijack filtering and no transit filtering properties for good measure. So in our evaluation, we wanted to also make sure we could take advantage of the parallelism that Timepiece offers us. And so we looked at doing this on a Microsoft Azure VM with 96 CPUs. And I'll start off by first talking about kind of how the actual annotation burden looks. So for each of these benchmarks, we had to write a little around 100 lines of C# code just to sort of provide some harnessing and defining the semantics. And then our actual annotations were very, very small burden. So at most about 21 lines of code to describe the annotations across every node in these examples. And most of these examples, all the fat tree examples, for instance, had a lot of nodes. So this is great compared to the size of our networks. And if you look at the actual verification time, monolithic verification, which is just happening on one thread, times out for almost all of our examples after over 2 hours. Only our simplest reachability benchmark is completable in 14 seconds. And modular verification scales a lot better. I mean, for this reachability case, which is so simple, it doesn't improve. But for all the other more complex examples, you can see that modular verification completes in a reasonable amount of time, taking at most 20 minutes for our path length benchmark, which requires more complex solver theories to solve. So I'm going to drill in a little more just on the hijack filtering benchmark that we have. And so hijack filtering is a particular property of interest in these networks because you can have cases where a hijacker, some external neighbor, sends you a route into your network that claims it has an IP prefix which it doesn't actually own. And this has caused a lot of famous internet outages over the years. And to test this out, what we did was we looked at a data center network where we had a legitimate route, E19, that sent some symbolically chosen IP prefix, and we had a hijacker H, which sent some symbolically chosen route, which we tagged as true. And we filtered the routes from H if they were for prefix P, and we wanted to check that eventually all the nodes should have routes for prefix P which are not tagged. So the actual interfaces that we had to write to do this composed both a globally and an until operator. And so we had to say that eventually, using this until operator, according to a time proportional to the distance from our legitimate destination, the nodes would have an internally reachable route for prefix P. And we also wanted to say that at all points in time, using this globally operator, nodes should not use hijacking routes. So if they have a route for prefix P, it should not be tagged. So I'll now get into a little bit about how fast this actually ran. So here you can see on the x-axis the number of nodes, and on the y-axis the verification time on a log scale. And you can see right away with this red line on the top that monolithic verification times out really fast at only 80 nodes, but Timepiece is able to scale all the way up to taking just over a little over 2 minutes, again, parallelized over 96 CPUs for our 2,000 node benchmark. And the actual verification time for any individual node is even better. 99% of our nodes complete their checks in under 5 seconds. And this is because the verification time has become proportional to the degree of the node because of these inductive checks, as opposed to the entire size of the whole network. So to take away, I hope I've convinced you that these big, complex control planes need these modular tools, and that temporal invariants provide a correct basis for modular verification. And we saw that we were able to use these to scale to thousands of nodes and complex policies, and you can read our paper to learn more about that. And here's a QR code. Also, I'm looking for a job. So thank you very much, and I'll take questions now.
Reminder that we have a microphone here in the middle of the room. If you have any questions, just come forward and line up here in front of the microphone. So I have a question. It seems like you are requiring the users to annotate these modules. And so I understand that this verification you make the verification modular. But does this mean that the user have to think about globally about what these nodes are interacting with each other to provide this environment that they are annotating?
Yeah, so the question was, does this mean that the user has to provide invariants and to gain these speedups? And so yes, so right now we are requiring the user to provide the invariant. You can imagine that inference techniques could also be used for this kind of system to infer invariants. But as we saw in our evaluation, the actual burden on the user to construct these invariants is relatively small. They only need to write a couple lines of code, and they gain a lot from writing these invariants of their system because if they ever want to update the system in the future, they can use these invariants to ensure that they haven't broken something.
Okay, thank you.
Hi, I'm Aarti from the University of Utah. I think I missed something early on, and I'm hoping you can explain it to me. So does Timepiece, are you trying to verify a particular configuration of the control plane at a particular point in time, or are you verifying the possible evolutions of the control plane over time as routes are broadcast and distributed throughout the system?
Great. So if I understood the question correctly, you're asking about, are we verifying the configurations sort of at a particular point in time? Right. So what we have is the configurations are written, they're static, and we're doing a static verification. But the configurations are going to describe how the network should update and eventually converge to a solution. And so there's another suite of tools, the data plane verification tools, which will then take this control plane to figure out how traffic is being handled. But what we're looking at is we're imagining you have a clear idea of who are the actors in your system, the different routers that are connected. And if you want to represent external neighbors that you're connected to, you can use, since we're using SMT, you can use symbolic values to capture possible behaviors they'll have. But yeah, we're working in a system where you're modeling that whole process of the control plane passing these routes around until you eventually converge to a solution.
Okay, thank you.
I have another question, which is follow-up of my previous question. So suppose now that your control plane has changed, you have updated your configuration. How much effort do you think that would be for updating the invariants?
That's a great question. So the question is, how much effort might it be to update your invariants after you've made a change to your control plane? So it'll depend, of course, on how you've written your invariants. There is a previous work where you had to provide exactly the converged route that the network would reach to do this modular verification. And so that is obviously very brittle, because that could change quite drastically with an update. But Timepiece is able to let you write very general predicates that can describe a very, very large space of possible routes. And so if you write your predicates well, obviously that can be a little difficult to do sometimes, but if you write them well, then they should require minimal actual changes to make an update to your system.
Okay, thank you. Yeah. Okay, if there's no question, let's thank our speaker again. And remember,